So we're going to look at how to divide polynomials. Remember, a polynomial is just a combination of x's, or variables in general, and numbers all added and subtracted together. But before we do that, we want to divide normal numbers and do a quick review on long division, because the process of long division with normal numbers is very similar to the process of division of polynomials. So we have two numbers up here, basic numbers. And when you're doing long division, you look at the leading digit for each inside and outside number. So on the outside, I just have one digit, that's 3. On the inside, my leading digit is 4, so that's the one I'm going to work with first. I'm going to say, how many times does 3 fit into 4? Or put another way, what can I multiply 3 by so I get as close to 4 as possible without going over? And that turns out to be 1. If I multiplied it by 2, I'd have a 6, and 6 would be more than 4, so I can't do 2, stuck with 1. And then I take the top number times the outside number, so 1 times 3, that gives me a 3. I subtract, and I get a 1. And then I bring down the next digit, in this case it's the 5, and I go through the process again. 3 goes into 15 how many times? Or put another way, 3 times what gets me as close to 15 as possible without going over, and that turns out to be a 5. And 5 times 3 is 15. Subtract and get a 0 this time. But we have one more digit to go, so we're going to bring that down and then ask ourselves, how many times does 3 go into 9? And again, it turns out to be 3 times. So 3 times 3, that's 9. Subtract, and a 0. So my remainder is 0, which is nice. So my answer then is the quotient 153. Now, a side note here that will come into play later on is that what this actually is saying is 3 times 153 gets me 459. So division is kind of a fancy way of factoring. I'm basically factoring out a 3 from 459, and the bones of what's left, that's my 153. And again, that will come into play in this example here. But that's how we divide normal numbers with long division. To divide polynomials with long division, again, it's a very similar process. We just have some variables in the mix instead. So let's look at one. We have x cubed plus 5x squared minus 12x minus 36, all divided by x minus 3. So just like with long division, where we were looking at the leading digit, for long division with polynomials, we're going to look at the leading term. The leading term is the term that has the biggest exponent on the variable. So on the inside, the leading term is x cubed, because 3 is the biggest exponent that the x has, so x cubed would be the leading term. On the outside, the leading term is just the x, because there's no other variable there. The minus 3 is a constant, so x would be my leading term, because I'm mainly focused on the variables. So I'm going to ask myself, when I long divide, how do I make the outside leading term the same as the inside leading term? So in this case, I'm going to ask myself, how do I make this x equal to this x cubed? What do I need to multiply that x by to make it equal to x cubed? And it turns out I need to multiply it by an x squared, because x squared times x is indeed x cubed. It gets me to that term without going over. So I'm going to put an x squared on top. And here's the first key about dividing polynomials, is that my top number is going to be multiplied to both outside terms. So I'm going to take x squared times x and get x cubed. I'm going to take x squared times minus 3 and get minus 3x squared. So I do it to both outside terms, not just the first one. I'm going to remove some clutter here, that way that doesn't stay there. Then, just like with long division with the normal numbers, I'm going to take these two expressions and I'm going to subtract them. This is just like we did with the normal numbers, where we did 4 minus 3, and then 15 minus 15, and then 9 minus 9. We subtract the inside expressions from each other. X cubed minus x cubed is 0. That's good. In fact, when you're doing long division with polynomials, the first terms of each of your subtraction pieces should always cancel. It should always make a 0. If they don't, that means your top number is not correct. You didn't multiply by the correct value. Then I have 5x squared minus negative 3x squared. Again, be very careful here because we're saying minus negative. So what this is actually saying is 5x squared plus 3x squared, which would be an 8x squared. Because again, we have that double negative here and here, which makes it into a plus. Then we're going to drop down the minus 12x. And we're going to go through the process again. So now my leading digit is 8x squared on the inside. So I'm going to ask myself, how do I get an x to be an 8x squared? Well, I need to multiply by the 8 first. And then I need to multiply it by an x. That would make the x squared. So multiply by 8 and x. Write that up top there. Then I'm going to go ahead and do my multiplication for my outside term. So 8x times x is 8x squared. 8x times negative 3 is negative 24x. I'm going to go ahead and subtract these two and see what I get. So 8x squared minus 8x squared is 0. Again, that's good. My first term should cancel. Negative 12x minus negative 24. Again, we hear ourselves have this double negative here. So negative 12 minus negative 24 is like negative 12 plus 24, which is positive 12x. Then I bring down my last term here, and I run through the process again. So how do I get an x to be a 12x? Well, this time all I need is just a 12, because 12 times x would get me 12x right away. And then I go through the multiplication one more time. 12 times x is 12x. 12 times negative 3 is minus 36. I subtract. And lucky for me, these all cancel. So I'll be left with 0 here. I'll be left with 0 here, because remember, minus negative 36 is like positive 36. And so I have a remainder of 0. Now, the way I write my answer is a little different, though, because when normal numbers, all I did was I wrote the quotient. With polynomials, what I'm going to do is I'm going to write x minus 3, which is what I divided by, and then what was left, x squared plus 8x plus 12. So with polynomials, division is more like a special form of factoring almost. You want to see, if I take out an x minus 3, what's the bones of what's left for that polynomial there, which is why you write them both. You write what you divided by and what the answer you got is. So x minus 3 times x squared plus 8x plus 12. And if I want to, I can even factor x squared plus 8x plus 12 possibly. Although, yeah, you can do 6 and 2 and factor that. But you don't need to do that unless your instructor tells you to. So that's what happens when we have a nice division. But what happens if we have a remainder? Because remainders can get a little tricky in polynomial division. The way you write them is a little bit strange. It's not necessarily too different than normal numbers, but we're not used to writing remainders for normal numbers in a very conventional way. So let's take a look at one more example here. Long division also has one key detail that a lot of people miss their first time when they're getting used to these problems. If you look here, it's not written in long division form yet. It says x to the fourth minus 2x squared plus 3 divided by x plus 4. So before we actually do our long division, our inside polynomial, which will be this one right here, that's the one that's going to go on the inside, that polynomial has to have its exponents be in descending order without skipping any numbers. What that means is that the exponent on the variables should go in order from biggest to smallest, and they should not skip any values. So I'm going to write a side example here real quick to kind of show you what I mean. If I had this, x squared plus 2x cubed plus 10x. That is not in descending order. The reason being is because if I look at the exponents on the variables, I have 2, 3, and then if you don't see the exponent, you assume there's a 1 there, so I have 2, 3, 1. That's not in order from biggest to smallest. In order to be from biggest to smallest, I would have to rearrange this and write like this. 2x cubed plus x squared plus 10x. And again, there's a little 1 on top of this x if you want. So now it goes 3, 2, 1. They're all in order from biggest to smallest. I haven't changed the value of the polynomial. It's still the exact same polynomial. It's just rearranged so that the exponents go in the proper order. Now, the second condition was that they don't skip an exponent as well. So I don't go 3, 1. I go 3, 2, 1. So that's a problem with the polynomial we have in our problem, is that not only is it missing some terms, it's missing 2 of them. It's missing an x cubed and an x. At the moment, it does go in order. It goes 4, 2, and then that 3 has an x to the 0 there. If you want to, you can write it in. This is x to the 0 power. Most people don't write that in there because it's not needed, but if it helps you see the order, you can. But I'm still missing an x cubed, I'm still missing an x. So how do I rectify that? How do I adjust for that? Well, it's actually a very elegant situation or solution here. What you do is you put your stuff in order, x to the 4th, but every time you come across an exponent you're missing, you plug in a 0 coefficient for it. So it'd be x to the 4th plus 0 x cubed minus 2x squared plus 0x plus 3, or again, you can write 3 times x to the 0 if you want, divided by x plus 4. So now I have my exponents in descending order. They go 4, 3, 2, 1, 0. But I haven't changed the value of the polynomial at all, because 0x cubed is still, in essence, just 0, and adding a 0 doesn't change the value to anything. So mainly what these zeros are here for is to make sure my numbers are aligned correctly. That way I don't have to do more work in the middle of the problem. I have it all set and ready to go. I can just follow it step by step by step as usual. So let's go ahead and set this up for long division here. I'm going to put my big number on the inside. I mean, a big polynomial, I should say, on the inside. Minus 2x squared plus 0x plus 3. Extend this bar a little bit here. And then my binomial is the one that goes on the outside. And then from here on out, it's just the exact same process we did with the other example. So let me give myself some space here. Check my leading terms, get them to be equal, subtract and bring it on through. So how do I make an x into an x to the 4th? Well, I multiply it by an x cubed. Okay. Let me erase those lines there real quick. That way they don't get in the way of the work. So let's see what I'd have then. I'd have an x to the 4th. I'd have a 4x cubed, because remember that x cubed gets multiplied to both outside terms. I would subtract these. My first pieces would cancel. That's good. They should. Be careful with your negatives here. 0 minus 4 is negative 4x cubed. Then we bring down the next term. So minus 2x squared. And we go through the process again. So how do I get an x to be a negative 4x cubed? Well, it needs a negative 4, and it needs 2 more x's. So multiply that through. Negative 4x squared times x is negative 4x cubed. That's good. They should match. Negative 4x squared times positive 4, that's negative 16x squared. Subtract these. First terms cancel. It's always good. Negative 2 minus negative 16. Again, we have that issue of having a double negative. So negative 2 minus 16 is like negative 2 plus 16, which would be positive 14x squared. I bring down my next term. So this 0x is brought down, even though it is a 0x, it is still brought down because it is still part of my problem. Go through the process once more. How do I make an x into a 14x squared? Well, that means it needs a 14 and another x. So I'm going to multiply it by 14x. Multiply 14x by x. Let's see what I get here. 14x times x would be positive 14x. That's good. 14x squared, rather. 14x times positive 4 would be 56x. Subtract these. 14x squared minus 14x squared gives me a nice 0. 0 minus 56x is negative 56x. Again, being very careful with my negatives. Drop down my next term. And it looks like I can do this one more time. So how do I get an x to be a negative 56x? Well, I need to put and multiply it by a negative 56. So I'd have negative 56x here. Negative 56 times 4 is negative 224. We subtract these. And unlike last time, even though the first two terms do cancel, so these cancel, 3 minus negative 24 isn't 0, negative 224, sorry. 3 minus negative 224 isn't 0, it is 227. So we have a remainder this time, and the way we write our remainder is kind of special. So I'm going to start out by writing everything like I did usually. So I'm going to give myself some space here. I divided by x plus 4, so I'll start with that, x plus 4. Then I'm going to write down my quotient, which is a rather large quotient, but we can still write it down. So if I scroll up here just a tad, so we can kind of see it a little bit. We have x cubed, a little bit more. There we go. We have x cubed minus 4x squared plus 14x minus 56. Curve it down there a little bit so it doesn't hit the line. And then how do I get my remainder in here? Well, my remainder is 227. And that's basically the part I couldn't divide. I could divide everything else. I just couldn't divide out that 227. So the way I record that is I say plus 227 over x plus 4 over what I'm dividing by. What that does is it tells the person that I successfully divided everything else in the problem except for that last little piece there. So that last little piece is still left to be divided, so I'm going to leave it as basically an unsolved division piece. That is the part that I have yet to solve, that 22 or 227. So I'm going to leave it like that, divided by x plus 4. So the process for long division essentially goes, write your polynomial in descending order without skipping any numbers. Find out your leading terms, figure out what you need to multiply by to get them to be the same, and then multiply, subtract, drop, repeat. Sounds like a long process, and it looks like a long process when I do it this way, but if you do it without explaining each step, then it goes a lot faster. Once you get used to it, just make sure, as always, to watch your negatives. Thank you for watching. Hope you have a good day.